So, hello guys. Today we are going to discuss all the problems of today's bi-weekly contest, and yeah, let's get started. The first, if we talk about the first problem, in first problem, I'll tell you the statement in short. So basically, we are given a price array, and we have the price of various chocolates with us, and we have some money with us, and we have to buy exactly two chocolates in such a way that we have some non-negative leftover money. So we have to minimize the sum of the prices of the two chocolates that we buy. So basically, we have n number of chocolates. We have the price for each chocolate, and we have to buy exactly two chocolates, out of which the two chocolates that we buy, the cumulative sum of both the chocolates should be minimized, and the and we should have some money left over after purchasing those two chocolates. So if we look at the any example like 1 to 2 and money is 3. So see, if we have three chocolates, one of price 1 and two of price 2, and our money that we have is 3. So this is already a sorted array, but we'll try to look at it in a different way. So we could have been given chocolates in any order. So since we have to always choose, since we have to minimize the sum of the chocolates that we purchase, so we try to add greedy, and by greedy we'll basically sort the array. After sorting the array, we'll take the two smallest elements, because those two smallest elements will assume or will always have the minimum sum possible. Like in this case, 1 plus 2 is 3, and the money we have is 3. So if our total sum of purchasing is less than equal to our money, then we are sure that we can purchase it. But if our total sum of the two minimum elements is greater than money, then we are purchasing items which are more than our budget, which is not possible. In that case, we have to return money. So in this case, our answer will be money minus 3, which is equal to 0. But if we consider the second case, 3 to 3 and 3 to 3, and money is still 3, then if we sort the array, we'll have 2, 3 and 3. Picking the top two smallest elements, the total is basically 5, which is greater than our money, which is budget. So we return money, as it is expected in the question, return money. So, and since it is saying that some non-negative integer, so our money can be equal to a target. In that case, our leftover money would be non-negative, as in case 0. But if it would have been positive, then equal to 0 would have not been, the money equal to the total would not have been equal considered. So that's about this problem. Let's move to the second problem. So yeah. In the next problem, basically we are given a string, and we have some words in the dictionary, and we have to we have to partition the string optimally in such a way that each substring is a part of, or is a word which is occurring in dictionary, and there could be some substrings of characters that are not part of the dictionary, and we have to minimize the number of extra characters that are basically cannot be part of the dictionary. So this is the whole problem. Like if we talk about in this example, like if we consider, like, let me clear this up. Yeah, if we take this example, LeetCode, Leet's code. Okay, so and our dictionary is basically LeetCode and LeetCode. So basically, in this example, they have partitioned according to this. They have partitioned this part, and they have partitioned this part. The Leet basically belongs to the dictionary, and similarly code also belongs to this dictionary. So only one extra character is left, which is the most minimum number. And if we consider this example, say hello world, and in this example, we can say that they have partitioned like this: hello and world. The hello exists in the dictionary and world exists, and minimum number of characters are 3. So if we look at the constraints, the number of constraints are less. They are almost 50, And since constraints are small, we can of course think of um, three possible scenarios. Like any problem could be solved in three ways with small number of constraints. One is recursion, another is one is recursion, another is dynamic programming, and the third could be bit masking. Bit masking doesn't seem, of course, any recursion is simply a bit mask because all possible scenarios are basically subsets of any string, of any binary string. So yeah, so recursion of course comes to our mind because how does recursion comes to our mind? Because like if we consider the example of Leet's code, Leet's code. Okay, so we try, since the n is small, so we try all possible scenarios. Like what our aim would be, we try to partition at every level as possible. Like we try to partition this, we try to partition after this character and check if this portion of the string belongs to dictionary or not. See, you see that L does not belong to the dictionary. Okay, so we now have a new subproblem of solving this. Since L cannot be part of a dictionary, so it will be act as an extra character. It will act as an extra character. Similarly, if I partition along LE, then LE does not belong to the dictionary, so we have two extra characters, 2 plus whatever be the answer of this particular string. So we have to apply the same logic on this smaller subproblem. So 2 plus whatever be the answer of each code. Similarly, if we create a partition this, then LEE doesn't exist in the dictionary, so we have three characters extra that cannot be part of the dictionary anytime, and we have to solve this subproblem. But there can be another scenario. If a partition along this time, we see that Leet is a part of dictionary, so this time our recursion will be somewhat different. Our recursion will be, now since Leet belongs to the dictionary, we'll simply have to call the recursive function for S code, as there are no extra characters left. Yeah, so this is the simple recursion which we'll have to use. And first of all, let me show you the code of first problem also. Yeah, so in the first problem, we'll simply sort the prices, then we'll take the minimum two prices greedily. If our budget which is the money is greater than equal to total, then we return money minus total, else we return money. If we talk about the second problem, okay, and basically we have also, of course, it should pass. The recursion is enough to pass because of the small constraints, but we have used DP here. Basically, how we have used DP is simple to recognize. See, so what we have basically done here is, like, let me show you. Okay, so our DP basically, first of all, we check upon our recursion. Okay, so first of all, we have declared n. We have inserted all the elements of the dictionary, or all the strings into a dictionary, and assigned map of it is equal to 1. So all the words in the dictionary are now marked with 1. Okay, so now what we have done is, we have basically called the function f. What we have done is, for every I, let's say our I is here. Okay, let's say our I is here. Let's say our I is here initially. Then we'll consider all j starting from I, and we'll keep on incrementing j to every character, and we'll try to consider j as the partition, and for each I we'll select all the j's, and the substring between I and j will be one such string, and we'll check if it can be consider extra characters, or is it present in the dictionary. Like if I go from I to j, then the substring I to j here is L. It does not belong to our dictionary. Then we'll check for the next j, and so our substring will be LE. Then our substring will be LEE. Then our substring will be LEET. Then our substring will be LEETJ. So what we have done is basically, we have iterated j from I till the end of the string, and we have considered the substring j minus I plus 1. So this line is basically, if we are let's say if our j is here, so we have considered this much substring and considered a partition here. So at any j, we have considered a partition from I to j. So this string current basically store like this string. So if this string belongs to our dictionary, then we have to just simply call the recursive function for this string. And since this belongs to our dictionary, so they do not contribute to the extra characters. So that's why it works. So hence we have simply considered answer is min of answer comma the recursive function recursive call for the next optimal suboptimal problem. Else, like in this case, leets is not a part of the substring. So these are the 5 characters which will always remain extra, and then we have to call the recursive function for this. So basically we have added this much length, these will be contributed to our minimum number of characters, extra characters, and then we have called the recursive function for this. And simply then we have simply memoized a solution. How we have memoized by how much states will be considered in DP. It's simple to notice that in this recursive function only I is changing and only the state of I is being changed, so we could have a 1D DP. Hence we have just considered the max possible length of the string, which is 50, and hence we have taken a DP of size 55 and memoized a solution. Yeah, we could have also considered top to bottom or bottom to top. Both approaches are correct. Yeah. So this is all about the second problem. Then we move to the third problem. Third problem is of course a simple problem because not much to like. It's just like a 0-1 knapsack. Yeah. So in this problem, basically we are given an array. We have to choose a subsequence of elements such that their product is maximized. Now, of course, if product is maximized, yeah. So it's a simple question. Like if I consider like 3 minus 1 minus 5 2 5 9. Let me see it's recording or not. Yeah, it's recording. Okay. 2 5 9 minus 3 minus 1 minus 5 2 5 and 9. Okay. So in this problem, first we see the constraints, and the constraints are pretty small. So of course a recursion comes into the picture. Recursion of course comes into the picture because since it's a subsequence problem, we have two options. Either we'll take that particular element or we'll not take that particular element. Okay, so like we have two options. Like we can either take 3 or not take 3. Now we come to minus 1. We can take minus 1. If we take minus 1, then we have product as minus 3. And if we don't take it, then our product is 3. If we take minus 1, then we have product as minus 1. And if we don't take a product, we have nothing. So at each step, we have two options. Either we can take an element or not take an element. So it's a simple DP problem. So not a simple recursive problem. We could have memoized also, but since the constraints are pretty small, like in the previous question, it was like n is equal to 50. So there could be chances of like a buffer overflow or TLE. So it was memoized, but there is no such need here. Like we could of course memorize it because memorize it in terms of like, let's first look at the code. Okay, so simply we have defined I as a starting point and 1 as the product. Initially, if we don't take any element, the product is 1. First of all, this corresponds to not taking an element. So if we don't consider the ith element, then what is the maximum product of the next set of elements? But if we take the ith element, then our product will be multiplied, the current product will be multiplied with the nums of I, and then we'll take the answer as max of answer comma product. Why we have taken the answer here? Because like we should not consider answer as after this particular line, because like if we have a positive number, so product will be increased, but after this line we could have a negative number also, so product could have been decreased. So at any instance, if we take the ith element, so let it be considered as one of the options for the maximum answer. Yeah, so that's why we have taken answer is max of answer comma product, and then we have called a recursive function for the next set of elements. So it's simple recursion, and yeah, that's pretty it. Yeah, it's pretty much it. Yeah. Then comes the fourth problem. Yeah, so basically this was an easy problem. Like the main problem, the reason why I could not do because was just of one or because of just two edge cases, yeah, which I should have been considered, but yeah, I could not, and it was not, of course, a hard problem. It was not, of course, a hard problem. Yeah. So let's look at it. Sorry. So what have been given here is like, okay. So let's consider, like, we have been given an array, and we have been given some elements in it, and we can jump from any particular index I to any particular index j if both of the elements at those indices have GCD greater than 1. So like, and then we have to find, is it possible for every pair of indices I and j, that I is less than j, to reach from I to j using a sequence of traversals. Like, if we consider this example 2 3 6, so 2 3 6. So first, let's say I is this and j is this. So can we jump from 2 to 3? Yes, not directly, because GCD of 2 and 3 is 1, but we can have a certain set of steps. Like, from 2 we can jump to 6, because GCD of 2 and 6, GCD here is 2, which is greater and not equal to 1. Then from 6 we can jump to 3, GCD again is equal to 3, and we have reached from 2 to 3 indirectly by an element. Okay, so by an element, yeah. So this is possible, this is always true. And if we consider the elements I to j, 2 to 6 we can of course reach, and from, if we consider I this and j this, to 3 to 6 we can reach. So for every pair of elements we can reach, so hence in this case the answer is true. Let me consider one more example. Yeah, let me consider this example. So 4 3 12 and 8. Let me write it down only. 4 3 12 and 8. Okay, so so if we consider these two elements, we cannot reach from 4 to 3 directly, because GCD is 1, but from 4 we can go to 12, from 12 we can go to 3, because GCD is 4 and here GCD is 3. From 4 to 12 we can directly reach, as their GCD is not equal to 1. From 4 to 8 also we can reach. From 3 to 12 we can reach. From 3 to 8, now this is interesting. From 3 we can go to 12. From 12 we can go to 8. GCD is 3 and GCD is 4. Yeah, so not equal to 1. So we can reach, and from 12 to 8 we can of course reach, because the GCD of course is 4. Yeah, so not equal to 0. So we can reach from every element to every other element. So if we look at the constraints, the nums total number of elements 10 raised to the power 5, and each element belongs from 1 to 10 raised to the power 5. So what comes to our mind basically? Let's consider this example only. 4 3 12 and 8. 4 3 12 and 8. Now, okay. So what can be our approach in this problem? Okay, so if we two elements, let's say x and let's say element y, if we need to go from x to y, so if they have something common, let's say this element be g, and then we can reach from this. Okay, so this means that if x and y have a, let's say, an element as GCD, then that particular GCD is a factor of x also, and that particular GCD is a factor of y also. So if we reach from x to y, like if let's say two elements x and y have a GCD, then that GCD is a factor of x also, and that GCD is a factor of y also. So we'll use the concept here only. So we'll use this concept here. So if we consider 4, let's say 4, so what are the factors of 4? What are the factors of 4? Okay, so 1, 2 and 4. What are the factors of 3? 1 and 3. What are the factors of 12? 1, 2, 3, 4, 6 and 12. And what are the factors of 8? 1, 2, 4, 1, 2, 4 and 8. Okay. So if we take a close look, 4 has factors as 1, 2 and 4. Yeah, 3 have factors 1 and 3, 12 have factors this. So if we look at 12, we have 4. 4 is a part of this. 4 belongs to our current set of numbers. Then we have 3. 3 also belongs to the current set of numbers. So from 12, we have 4 and we have 3. So we can reach from 4 to 12. We can reach from 3 to 12. And we can also reach from 4 to 3 via this 12. So this concept is now somewhat similar to disjoint set union because if two elements are connected to this, if multiple elements are connected to the same component, then they are reachable. Like if 12 is connected to 4, so we can reach from 4 to 12 or 12 to 4. Now if 3 is connected to 12, then we can reach from 12 to 3, or we can reach from 3 to 12. Also we can reach from 3 to 4. So since element belong to the same component, we can reach from any particular element to any other particular element as desired. Yeah. So how we have used disjoint set union, let's talk about that. Okay, so let me clear it. So if we consider 12, so first of all we'll use a map and mark all our elements that are present. So 4 means 1, 3 means 1, 12 means 1, and 8 means 1. It means that these elements are present in our original array. So if we talk about 12, what are its factors? Let's say 2 is its factor. We'll not consider 1 as a factor because the GCD can't be 1. So 2 is our factor. So since 12 and 2 are a factor of each other, so we'll use the DSU concept and merge 12 and 2. 12 and 2. Next comes, so we have merged 2 and 12. Next comes the element 3. So we merge 12 and 3. So we merge 12 and 3. So this merging is done using disjoint set union. Then comes 4. 4 and 12 are merged. 4 and 6. 6 are merged. Then comes 12. We won't consider 12 as that element because it belongs to itself. So yeah. So this we have formed a disjoint set using we have formed a component using DSU. Let's consider the next element. Let's say we consider 4. So it has its GCD as 2. We won't consider itself 4. So 4 is of course connected. Like 4 and 2 are connected. 4 and 2 are of course connected to each other. They belong to the same component, so we won't merge them. So that's why we use the concept of getting the absolute parent, because if two elements whose absolute parent are same, we won't merge them. And if they're not same, then we'll merge using union by rank and union by path compression so as to optimize the merging. Yeah. So if we consider 8, let's say if we consider 8, so 8 have factors 2, so we'll merge 2 and 8. Now see, 8 and 2 does not have, so what we did, 8 has a factor 2. So we see 2 and 8 do not have same absolute parents, like 8 does not belong to this particular component. So we'll basically merge 2 and 8 now. So now 8 is also part of this whole component. Then comes 2 and 4. 4 and 8 are not parts of the same component, so they are not connected to each other. So what we just saw that by connecting 8, now we can reach from any particular element, like we can reach from 3 to 8 because now 3 and 8 belong to the same component via these components, via these elements. So this is why DSU is important here. So this is exactly the code that what we have done. So basically this is the DSU standard DSU code. We have used rank compression, and we have used this code to get the absolute parent, and we have merged childs based upon the rank by path compression. And then in the code we have basically first used map, and then we have found the maximum element in nums plus 1 based indexing, and then we have called DSU and initialized DSU, and we have first marked all the elements in the map using map, like these particular elements belong to the original nums array. Now for each element, let's say we denoted by x, we have tried to find all its factors. We have tried to find all the factors. Like if xj is not a factor of x, then we continue x. we'll consider that particular element and complement of it. If both are same, like if factor of 4, like one factor of 4 is 2 and other factor is also 2, then we'll consider it only once and then we'll merge x and the first child. Else we'll merge the first child with x and also we'll merge the second factor with x. This is what means, like if we talk about 12, let's say 12 has a factor 3. So we see that 3, 12 mod 3 is 0. So let's, here fst is 3 and snd will be second factor, like first factor is 3, the other factor will be 12 by 3, which is 4. So we have done the same chart, we have merged x with first factor and x with second factor. So 12 is merged with 3 and 12 is merged with, and 12 and 4 is also merged with it, and 12 is also merged with its complement 4. Yeah, so we have merged both of them, and in this way we have formed all the connected components, like and so all the elements that belong to a particular component will be reachable, or will be accessible or can be converted into one another. Then we have used a vector parent for each element. If that particular element or ith index element or ith element belongs to our nums array, which is noted by this, then we have pushed its absolute parent. So like all the elements, we have considered all these elements and taken the absolute parent, which actually to whom group they belong to. So if all the elements absolute parent comes as same, it means that they belong to the same group, and hence each node is reachable to one another or from one another. Like we have basically sorted it and just checked if parent first element is equal to last, because if we sort any array and the first element is equal to the last element, it means that all the elements in the array are equal. This particular ensures that there is only one parent, and so all belong to the same group, and hence one node is reachable from another node, else we return false. Now the main problem that came in this question, I could not solve it because I could not think of these two corner cases which were pretty obvious. Like I could not solve, like it's a no need. Yeah, so we have to consider one problem, that if there is only one element in an array, let's say 12 or let's say 2, so it doesn't form any pair with any other element, so it's of course it's reachable. So that's why for n is equal to 1, answer is true. Now for one more case that a problem fails is like if we have an array of like 1 1 1, all ones. In this case what will happen? In this case what will happen, these loops won't run, and in this case we'll end up picking up one element in the parent array, but one, considering all ones, cannot be an answer because the GCD can never be equal to 1. That's why our problem fails for this, our solution fails for this case. And so we have to ensure that if maximum element is 2, which means that maximum element is 2, yani ki max element in the nums array is 1. So if max element is 1, so all the elements in the array are 1, it means that it is never possible. That's why return false. So these were the two edge cases because of which I could not solve the problem. So yeah, we should always take care of the corner edge cases while solving any such problem. Yeah, but I still have some doubts, like will it's of course a tight, I think it's a loose bound on the time limit, because if we consider a nums array of length 10 raised to the power 5 and all elements are 10 to the power 5, and so in that case our solution will run into 10 raised to the power times square root of 10 raised to the power 5, because finding all the factors of any element is square root of n. So 10 raised to the power 7.5 approx. It may pass or it may not pass. Like this was one solution that I implemented, and these two edge cases were the reason I could not solve the whole problem, and else all cases passed. Yeah, so it was frustrating, but yeah, I think of course learned something from it. Like we should consider all the possible scenarios, all the possible cases, and we should probably carefully look at the constraints for getting the approach and considering the corner cases. Yeah, so that was pretty it, and not a good rank, of course, not a good rank. Yeah, but still, I managed to score a rank of 2082 with one penalty. Yeah. So I think that was it for this contest. Yeah, I think hope you learned something from it, and of course it benefited me also. Yeah, so thank you. So till then, goodbye, and let's meet the next time. Bye.